Okay, good morning, girls.
Morning, teacher.
Okay, can someone give us a recap of what happened last week, what we discussed in the last lesson? Who is that?
44.
Okay.
Okay, we learned about the arrangement of particles in liquids, solids, and gases. Then we also said that the properties of the substances depend on the arrangement of the particles and how they are held together. Then teacher showed us that experiment of compression of liquids and gases, whereby the gases were easily compressed, but the liquids were not. He also told us to try it with a syringe at home. I tried mine and the syringe broke when I tried using the water. It broke because I was compressing it too hard. Then he also told us about the application of the incompressible nature of water. He said that soil erosion is one of the natural applications. Then he also, one of the students gave an example that it's used in hydraulic trains. Yeah, then we said something about a particle theory of matter, but I don't think we finished it.
Okay. Thank you so much, Crown. And you really ventured, and I believe that your hard work is going to pay off. That was, I think, almost what we discussed last season. We are talking about the different, we talked about liquids, gases being compressible and liquids not being compressible. We have talked about the applications of the incompressible, when liquids are incompressible, where we use them in hydraulic machines and so on and so forth. Though that was a little bit ahead of you, but it was one of the things that you must understand, that physics is basically an investigative subject, and we apply so many of those principles as we proceed. So I think going forward, unless anybody has anything else to add, want us to continue and add something in this lesson? Unless anyone has any other contribution, anyone with a contribution, anything that you want to add on to what we have been told? No one?
Yeah, there is no hand.
Okay. So, by the way, anybody who carried out the balloon, I came in a little bit late when Crown was presenting. Anybody who did the balloon, what they have observed about the balloon? Anyone who did the balloon experiment?
Vivian, Sandra, and
Sandra,
Newton.
yes.
I tried out the balloon experiment, and today it has reduced because when I blew it, it was a little bit, it was big, but now it is smaller than it was before.
So that is one of the things. Most of us have a tendency of believing that maybe that air escapes through the point where we tied that balloon, but in actual sense, that is not true. What happens is that the balloon, the air usually escapes through the tiny holes within the spaces of the balloon material, that fabric. So that implies that the particles of air have the ability to escape through very, very tiny invisible holes that exist within the balloon. So if you continue with that experiment and you're patient with that balloon, sooner or later, you may find that almost all the air has escaped out of that balloon. Is that okay? And that actually proves that most materials are made up of very small particles. So at Kunda, Vanessa, you have something to say?
Teacher, I'm asking why does the air like escape? Why does it escape?
Much as I'm trying to say, just like your skin, by the way, do you know that you sweat? Yeah?
Yes.
Yes.
Don't we
Yes.
sweat? So, but do we see visible holes in our skins? In our skin, do we see
Sometimes when it's hot,
eh?
sometimes when it's hot, there's some spots on your skin.
Okay, you can see those small, tiny goosebumps and so on. So usually your skin is almost behaving like that balloon fiber. However, the holes, the tiny holes within the balloon fiber are almost invisible. So air can escape through those tiny pores within the balloon fabric. That's what you are trying to say. Okay, it will be explained more as we read through your notes. Daniela?
Why does a balloon burst in grass?
Hey, in grass. But it is pricked and that air, when given that time to escape, the whole process of escaping, because of the too much pressure exerted by the escaping air, it is like all of you trying to stampede out of a very tiny outlet. When you try to stampede, basically there is a lot of chaos and a lot of pressure is exerted, and therefore the balloon fabric ends up tearing or bursting. Is that okay?
Teacher, could I also give an answer?
Yes, please.
Yes.
If you look at the grass, it has like hairy, like hair on it. So when the balloon goes onto the grass, it may not burst immediately, but the grass is like if you throw it in a hole filled with thorns, basically.
Exactly. The balloon fabric gets pierced, the air inside the balloon tries to escape at the same time through a very tiny outlet, and that too much pressure causes the balloon fabric to tear. So it bursts just like a car tire, etc. When a lot of air is trying to escape all of it at the same time, it is like a stampede. Do you know what a stampede is? Stampeding is?
Yes.
So all of you are trying to get out at the same time, yet the outlet you are trying to use is too tiny. You exert too much pressure, and in most cases you cause a stampede. So the air stampedes the fabric, and therefore it causes it to tear. And that's what causes the bursting.
Excuse me, teacher.
Yes?
There's something I also wanted to add on to that.
You can add?
I think the rate at which the balloon pops bases on the amount of pressure that's in the balloon. Let us say a balloon has a lot of pressure, that it has a lot of air in it, and like the minute it touches grass, it can pop, while the other balloons that like have little air in it and like it takes them time to pop because there's not that much pressure in them.
Thank you so much.
Yes, yeah.
There is Daniela. Say, Daniela, your arm is still up. Daniela?
Sorry, I forgot to lower it.
Okay. Let us try to go ahead in our notes. I'm going to share the screen and then we talk more. So I think we stopped somewhere here. We stopped there below that vehicle. We have that vehicle. That's where we stopped. So can we read it quickly? I'm asking who? Okay. I've been made to understand that some people, these notes that are displayed were read at a very high speed, and therefore we need to revisit them. So, 5 participants have their arms up. Who are these participants? See, I've never had Nanyanzi Ozana in 1K talk. So Nanyanzi Ozana, what do you want to tell us?
Yes.
Yeah?
Here it's saying the particle theory of matter.
So you want to read for us?
Yes, please.
Okay, please do.
Describing the composition of matter is not easy since the actual composition can only be
Inferred,
inferred rather
mhm.
than observed. Suppose you take a piece of charcoal and break it up into tiny pieces and then break these tiny pieces into dust. It is still charcoal. Then take the dust and further divide it until it is no longer visible. These invisible particles are still charcoal. Should I continue?
Yes, please, you are finishing that. We read that last time, but we're just referring to it to lay a good background for our continuation. Read the whole paragraph, please.
Yes. As early as 400 BC, the Greek philosopher Democritus thought that matter could be broken down until it can no longer be subdivided. He called these invisible particles atoms, from the Greek word meaning divisible. By observing how particles
read that Greek word properly.
Atoms.
Then from the Greek word meaning?
Not divisible.
Yeah, you had to jump that word, not divisible. An atom is not divisible. You cannot divide it any further. It is the tiniest particle. I hope that is clear. Okay?
Yes, teacher.
Okay.
Yes, teacher. By observing how particles behave in water and smoke, scientists developed a model to identify the composition of matter. Number one, all matter is made up of extremely tiny particles. There are spaces between the particles. 2, each pure substance has its own kind of particles, different from the particles of other substances. 3, particles.
No. Read that statement again. You are jumping.
Each pure substance has its own kind of particles, different from the particles of other pure substances.
Good. So don't jump words, we shall lose meaning. Is that okay?
Yes.
Okay.
The particles of matter attract each other. Number 4, particles are always moving or vibrating at fixed positions. 5, particles at a higher temperature move in brackets or vibrate. Say this word.
Vibrate faster.
Faster on average than particles at a lower temperature.
Okay. I hope, girls, you noted down those behaviors of the particles because they tell you, you notes. Those are very important characteristics of the behavior of the particles of any substance. I hope you captured that information.
Yes.
Have you captured it?
Yes, please, teacher.
Okay, please, whoever hasn't captured it, capture. That is one of the things that we're going to be talking about later. Okay, now can you continue reading?
Okay, these are
please.
there are things we experience in our daily life, which also explain that solids, liquids, and gases are made of small particles, which we cannot see with our naked eyes. For example, when your clothes are drying, or when sugar mixes or in brackets dissolves in water, we cannot see what is happening. Scientists use the idea of particles to explain what is happening. The particles are so small that we cannot see them. So, what do you think happens to the water particles when clothes dry? And to the sugar particles when they dissolve in the water? The water particles on your clothes escape into the air. The sugar particles get absorbed into the water.
Okay. Thank you. Because your network seems to have been now breaking, I think I'm going to pick up another reader. We had covered that last. We had read through. I hope now it is making more sense as we proceed. But let me pick up on another reader because your network seems to be having challenges. Another reader. Another reader sure of her network that doesn't break. Mr. Sally, you can pick for us another reader.
Okay, let's have Marianne Atwenda unmute and start.
If a rock breaks, it forms a fine powder of particles which are called dust. When you travel on a dusty road, you may have noticed that dust rises and stays in air for a long time and can also easily get inside the car or bus. Although you can see the dust with your naked eye, each grain of dust
And you're breaking.
even small. So should I start again?
Yes.
You do. We are giving you one chance, but I hope the network doesn't get spoiled. Read quickly, please.
If a rock breaks, it forms a fine powder of particles which we call dust. When you travel on a dusty road, you may have noticed that dust rises and stays in air for a long time and can also get inside the car or bus. Although you can see the dust with your naked eye, each grain of dust is made up of even smaller particles which you cannot see. It takes millions of small particles to make the grain of dust, which you can see smaller than grains of dust.
Okay.
We know that they exist because we breathe in air particles.
Stop there. That whole paragraph there is trying to explain to us that matter is made up of very tiny particles. In class, there is a certain form of dust as teachers write using chalk. Have you ever observed that dust chalk, especially on the blackboard? The chalk dust.
Yes.
Yes.
Okay. Actually, let me try to show you something here of our flow, how it looks like. I hope you can tap the screen. Yes, I think so. But let me unshare first. So I hope you can tap that screen. Do you see anything down on that floor there?
Yes, chalk dust.
Yes.
That is the, how does it form? How does it form? Hey.
Let's have the answer. Let's have Subika Thelma unmute and answer. Thelma. Thelma seems not to be there. Trouble Pal, unmute and.
I think the chalk dust is formed when, like, you can have a long piece of chalk, and as you're writing on the board, there is some friction that causes wear and tear. The chalk starts kind of breaking down into smaller pieces, and that's what forms the dust.
Who is Thelma? Thelma, you show me your photo. I really want to see you. This guy is just bright.
Trouble Pal.
It was Chirao. Okay, but I don't know Chirabo. Chirabo, you will show me your photo later. This is Chirabo. Let me, where is Chirabo? I want to see you. Video. Chirabo Pal.
Chirabo is shy.
But no, this girl is shy. Okay, but she has given us a very beautiful explanation for that formation of chalk dust. Okay, and exactly that's what happens to the dust that you have talked about with the cars. When the cars keep passing over a dusty road, they keep breaking down that dirt into tiny particles, forming dust. That dust has the ability to rise into air. It can escape and come into the vehicle itself. And then we see a lot of dust. So these cars need a lot of cleaning as they keep traveling. I think you see that dust forming on the dashboard and so on, even the seats. Sometimes if you're on a dusty road, you discover that those dust particles also enter your hair or your eyes and so on. I think you have ever traveled on a dusty road. Anybody who hasn't got that experience should get out of Uganda. Isn't it?
Yes.
So we have seen that actually matter is made up of tiny particles. I think that fact has been well established. So we want to go a little further in our notes, girls. So let us think about air. They are telling us to think about air. Can we pick another reader?
Okay, let's have someone who hasn't said Queen Victoria, unmute and submit and read. Queen Victoria.
Should I start?
Yes, please.
Okay. If a rock breaks, it forms a fine powder of particles which
we have moved out from there. Think about air, that's where we are.
Okay. Think about air. We cannot see air particles because they are very much smaller than grains of dust. We know that they exist because we breathe in air particles. We also feel the wind when many air particles are moving and hitting us.
Okay. Any other observation about the moving air? By the way, what is it called? When air is in motion, what name is given to it?
Wind.
It is wind, isn't it? Can you give me some of the effects of wind? When you know that there is a wind blowing, what happens? What do you see?
Wind raises dust.
Wind raises dust, number one.
Causes leaves to shake on leaves.
It shakes the leaves. Now that is okay. Number 2, 3.
It blows clothes.
It blows what?
Blows the clothes to dry.
You have ever put on that cloth and the wind has blown it. You know that kind of cloth, eh? So it blows clothes, it blows flags, and so on. So with that, those are the effects that in actual sense, there is an unseen wind or air that has the ability to even to cause forces and make other things move. I hope that is clear. I have 9 participants with their arms up. Are they making additions? Okay, if they are making addition, let us not fail them. Adeke Faith, what are you trying to tell us?
Actually, I wanted to read, but I've understood everything.
Very good. Crown, what are you trying to tell us?
Yes,
I wanted to know if the particle theory of matter is also called the kinetic theory of matter.
That is okay. It is called that.
It is the same
name. That is the name, the actual name. It is the kinetic theory of matter.
Okay, thank you.
Okay. Then there is the lemma.
Georgie, unmute and.
And there are 2 Georges. What is happening here? There is a Georgie Lena, there is a Georgie Lena. Who is the second one?
The second one must be an intruder.
So Georgie Lena, I hope this person does not abuse us at the end of the lesson.
Georgie, submit, your hand is up.
I just also wanted to read.
Oh, okay.
Whoever doesn't have any contribution, put down. But Lena, you have another person impersonating you. Who is that one? Yeah. So, Mr. Oluka, if you are in the background, please, we have two dual learners. I don't know who is the correct one and who is, I think the other one who can't say anything is the intruder. Okay, so we are trying to look at the evidence. What evidence is there for particles? What really shows us, what do scientists do to show that actually there are existence of particles, to explain the particulate nature of matter? So can we move Mr. Sali, pick us a reader?
Okay. Someone ready to read? Let's have someone who hasn't said anything. Okay, Shalom Walube, unmute and read.
What evidence is there for particles? We cannot see particles because they are too small, but scientists believe they exist. This is a scientific theory. Scientists think up theories to explain their observations. When they look for evidence to prove
read properly.
Then they look for evidence to prove that their theory is correct. Evidence is something that you can see or hear or touch that can be explained by the theory.
Okay.
The next activity provides some evidence for the particles. You will make an observation that can be explained by the theory of particles. Activity 3.3, investigating the evidence of particles using a balloon filled with air. Key question, how can we explain?
Can you let us keep, please observe when I tell you to read, you come back and read again, okay? But that activity is the one that we first discussed in the beginning. It is about a balloon, you blow in air and you observe it over the days. And I think already the people who have carried it out have observed that the balloon reduces in size, isn't it? Is that true?
Yes.
Especially the person who carried out that experiment or who was the balloon in her vicinity or neighborhood or very near her. The one who has observed that the size of the balloon is reducing. Can she tell us her experience quickly? Okay, she talked about it, but this is what is going to explain. So please continue the reading, but if possible, do that experiment and you see what we have been talking about. So read quickly. Please continue reading.
What you need, a balloon, string. What to do, blow up a balloon, tie the string tightly around the neck of the balloon many times. Look at the balloon every day to see if it has changed size. Did you see that the balloon gets smaller and smaller? This is because the air is escaping. How is it escaping? Can you think of an explanation why the balloon goes down? Here is an explanation that uses the theory of particles. Look at the picture in figure 3.6. It shows the rubber skin of the balloon. The skin is made up of rubber particles packed closely together. But there are places where the air particles can get out through holes between the rubber particles. The air particles inside the balloon are
Charity. Sasa ndio you still sasa ndio Charity, are you still there? Yes, Charlotte, unmute.
Teacher, am I still reading or not?
You have the notes. It seems we've lost Mr. Sanjay. I'm not seeing him. Okay, he's back. Yes, you can continue. Charlotte, you can continue.
So I don't have the book with me.
Okay, Mr. Sanjobe, are you back? Mr. Sanjobe, you are muted.
I am Schwarzenegger. I am back. Kari, we go. The girl, I hope she's done. I don't know what she was reading. Okay.
Yes.
Who was reading for us, please? I'm sorry, I had a breakage.
Shalom, she's still there.
Yes. Can you continue? I think you stopped around here. The air particles inside.
I had actually finished that page.
Hey, you finished from which? The air particles inside the balloon are constantly moving around and hitting the skin of the balloon. If you manage to get out of the balloon, I think we had finished that. Is that okay?
Yes.
Thank you so much for reading so, but then can you continue and finish your program until the next heading?
Okay. Solids and liquids are also made of particles. When we mix a cool drink, powder, in brackets a solid, in water, in brackets a liquid, we notice that the powder seems to disappear into the water. The water takes the color of the powder and tastes different. The next activity provides more evidence for particles. This time, the particles are in a liquid.
Now, can you tell me some of the things that we mix, especially at school and at home? I want us to talk about this practically from for me, I mix something, I'll give you an idea of one. Coffee, the rest I think is in your docket. One girl gives us her experience, she mixes what? And if possible, the color. Mr. Sally?
Yes.
You have 10 participants with arms up.
Okay, Janet, unmute and submit. Janet,
Teacher,
7.
at home, I mix milk and sugar.
Milk and sugar. And what is what does the eventual color?
It remains white.
The water wasn't white before.
She said sugar.
Oh, you said milk and sugar.
Yes.
So it remained white. So what changes? Something changes.
Maybe the taste.
Yes. So what happens? The milk, it becomes, in terms of taste?
It becomes sweeter.
Good. So those are the observations. Remember, you were scientists. You are making observations. That is number one. Thank you for that contribution. Another person mixes what?
Kayesu, unmute and submit.
Teacher, at school, you mix tongue. It's like juice, but in powdered form. So you mix it in water. You mix it in water. So if it's orange tongue, it becomes orange, and then it tastes like orange juice.
Orange juice. So the taste changes. That's very good. Anything else?
Okay, we can have Vivian Sandra. Vivian Sandra.
For me, I mix powdered milk and water, and when I mix the water becomes white, so it changes color. It takes the color of the powdered milk.
Very good. I think we have got sufficient examples. Now, the powdered milk, can you talk, especially that powder, when you have mixed it into the water, does it stay as powder? What happens to it? Or the tank, especially those powders that you mix, do they remain as powder?
Mary, unmute and respond.
No, the powder dissolves into the water.
The powders totally dissolve into the water and they disappear. Is that okay?
Yes.
Are we okay? So the process you have talked about dissolving. So particles can dissolve into each other. So even the small tiny powder particles that you are seeing have totally disappeared. And what is their effect? In most cases, their effect is that they can cause a change in color of the liquid in which you have mixed them in, isn't it? Okay, so I think we have seen some, we know that we do a lot of mixing. Nobody has talked about salt, but people also use salt. Sometimes we don't want all these things to become sweet, but we can serve that salty taste can also become good. And what happens, especially salt, what is the, what is talked about salt? In most cases, we are told that we are not supposed to eat raw salt. But what do we do to make that salt to disappear usually? What do we do? If we want that salt to dissolve very quickly, what do we do?
Okay, we have, let me have here, Atkunda Vanessa, unmute and answer.
You put like the raw salt in like hot water to make it dissolve faster.
Okay, so the rate of dissolving is increased by increase of what? The rate at which the salt will dissolve is increased if you increase what?
Atkunda, are you still there? Okay, let's give a chance to another person here. Crown, unmute.
I think if you increase the heat.
Can we get another word to represent that word which you're calling heat? There is another word.
Temperature.
Temperature. Okay, that's very good. The moment you increase the temperature, in most cases, the rate at which dissolving takes place increases also. So dissolving increases, rate of dissolving increases with increase in temperature. That's very good. So you are going to discover that when you put, for example, tea leaves in cold water, what will be the rate of dissolving?
Okay, Eunice.
Have you ever served the tea and that water was cold and your mom has not scolded you?
Yeah, teacher, the tea leaves like takes a long time to mix well with the
to dissolve into the tea. So in most cases, what do you do? You put tea leaves in very hot
water
so that you increase the rate of dissolving. That's very good, I hope. Is that okay? So I hope you have seen that. So let us read through that, investigating the evidence of particles using a liquid. Can we have somebody reading for us?
Elena, may you read for us?
Investigating evidence of particles using liquid. Key question: how do we know that solids and liquids are made of particles which are in a state of random motion? What you need: a crystal of potassium permanganate, a drop of ink, water, 2 small transparent containers. What to do: fill the containers with water and allow the water to settle. Carefully place a crystal of potassium permanganate in the water on one side of one container as shown in figure 3.6. At the same time, a friend must carefully place a drop of ink in the water on one side of the other container. Do not move the containers. Look at what happens to them during the rest of the lesson. Leave them overnight and look again. What is the difference between them?
Okay, so some of these experiments are best done at school. I hope you're together. But before we go ahead, what do you expect to have happened? For example, with a potassium permanganate, it is a crystal that has been placed at the bottom of the container. What do you expect to have happened?
Okay, Faith, Emmanuel. Faith.
I think once the crystal is placed in the water, it will dissolve.
Faith, we have little time.
She answered.
Yeah.
She answered. She answered.
She answered.
Yes.
I heard nothing.
Faith,
I said.
You
Yes.
said what?
I said that once a crystal is placed into the water, it will dissolve.
It will dissolve, and then what do you expect to see?
I
Anybody who
think
can add more to that answer?
Okay, Pamela.
Eh?
Pamela and mutant.
Okay.
Teacher, I think when the crystal of potassium permanganate is put in water, it will dissolve and the water will change the color, its color, and change the color of the crystal.
Okay. Usually the color will become a little bit purple, but we have been trying to look for these crystals of potassium permanganate. Usually they're around in the labs, but they are locked, unfortunately, where the storage. So for us, we are going to try to carry out this experiment. Potassium permanganate. Okay. Potassium permanganate, if we find it, we shall show you this experiment because it is something that you are supposed to see. But we have thought through and said maybe let us try tea leaves and we see because it may give us a good idea. Already you have told me that if tea leaves are put in cold water, they'll take long for that tea for them to dissolve. In actual sense, the color that of the water will take long to change if we place tea leaves in water when the water is cold. But so what we're going to try to do is to try to warm water and we put in our tea leaves and then we shall see what happens. So as we wait for the warm water, quickly, let us read what is below. Can we read what is below? Particles of a solid dissolved in water. Can you read that quickly, please?
Okay, let's have a travel pal. May you read?
What happened to the crystal of potassium permanganate? Did you see that crystal of potassium permanganate changed color of the water? This can be explained by the idea of particles. Each particle that leaves the crystal moves in between the particles of the water and spreads. You cannot see each particle because the particles are very, very small. When the particles of a substance spread from one region to another, the process is called diffusion. After some time, all the particles from the potassium permanganate crystal have spread evenly throughout the water to form a solution. This is why the crystal cannot be seen anymore. It has dissolved. Think of a colored liquid like ink. What would happen to the color of water if a drop of ink is put into a glass of water? The particles in the ink, which is a liquid, will also diffuse or spread throughout the water until the color becomes the same throughout the solution.
Okay, thank you so much. So the process of particles of one substance dissolving into particles of another substance is called diffusion. I hope that is clear. Diffusion is whereby particles of a substance spread from one region to another. Is that okay? So they spread, we have seen that potassium permanganate slowly spreads through the liquid until it is totally dissolved. So that process is what we refer to as diffusion is taking place. So that is what happens when you get your milk and you put it in your water. That's what happens when you put sugar or salt into a liquid, and the process is made faster by increasing the temperature of that solution. Is that okay? So the eventual mixture of any two particles is called, actually those that turn into liquid are what we refer to as solutions. I hope you know solutions in your chemistry. Is that okay? Is that okay, girls? The ladies have kept quiet. Is it me who is not being heard or what? Mr.
No,
Sali, girls.
You're very clear. There's only one hand of travel units.
Travel.
Teacher, I actually had a question.
Yes.
On the principle of tea leaves dissolving, how comes when you put tea leaves in water, they don't actually completely dissolve? Like there's still stuff.
The small leaves, but what happens with that? What do you see when you put tea leaves in water? What exactly happens?
The color of the water changes.
The color of the water changes. So there is an extract out of the tea leaves that is extracted out. Those small particles, much as the leaves themselves don't completely dissolve into the water, but there is something that is extracted out of the tea leaves.
Okay.
Isn't it?
Yes.
So some substances like sand, etc., much as they are powders, they don't totally dissolve. But if here the idea, because tea leaves don't totally dissolve, but what we want to use is a simple demonstration that in actual sense, there is some semi-dissolving of those tea leaves because something or a certain substance must be extracted out of them that changes the color of the water. Okay, so it is not the best. That's why we use potassium permanganate or salt or sugar, because those ones completely dissolve, isn't it?
Yes.
Okay, so I'm waiting simply for hot water. I'm going to put on a video and you see what happens here. We are simply going to stop, I think, at this experiment. We want to give you a simple idea of what we are talking about, though we are improvising, okay? So I hope you can see, I'm going to play the video. What is this? Do you see what I'm holding? Oh no. Do you see?
Maybe you can unshare the notes, Mr. Senove, or we can tap your window.
I can see that if they wanted, they would see.
Okay, they can tap the window, they can see.
I hope you see this. These are what do you think this is?
Someone unmute and work with the teacher. Someone put up your hand and okay, Vivian, Sandra.
I think those are tea leaves.
These are tea leaves, okay? So we are using tea leaves. So we have these two beakers. I hope you can see them. We are putting some tea leaves here, and we are putting another in that container. I use all of them. I think it is okay. That is what we have. Now, this is water. This is cold water, okay? So I am pouring cold water into this beaker. I hope that tea leaves will settle. They told us we should allow it to settle. Do you observe any change in the color? And now we are putting hot water in this system also. So tell us your observations.
Mr. Sanjove, you can pull the beakers towards yourself slightly. Yes, there.
Okay, so girls, tell us your observations.
Okay, Naila, unmute and share. Naila. Okay, let's have Mutamba, Primrose, unmute and share.
Teacher, the beaker with tea leaves and cold water has changed the color, but not as the beaker with the hot water.
Okay. So what is your conclusion?
Yeah, I think my conclusion could be that when temperature of liquid is increased, the solute or the substance that is to be dissolved will dissolve faster and change the color of the liquid, while the low temperature of the liquid will make the solute not dissolve faster.
Okay. So if I am to simplify your statement, you are simply telling us that we observe that there is dissolving of these tea leaves, though it is not complete, it is partial dissolving. And we discover that the rate of dissolving increases with the temperature. I think that those are the basic observations that we can make from these two beakers,
Yes.
isn't it? Okay.
Yeah.
So when substances dissolve, they can cause a change in color. However, a change in color is not a must for all substances. I hope you understand that.
Mr. Sanjove, we are not hearing you. Mr. Sanjove.
Yes, Evo. You want to unmute. I don't
No,
want to tell them to see color only as the only means of dissolving. Mr. Sali, what is my problem?
No, at some point we had lost you. We are not hearing you.
Hey. Okay, I said that with these particles, what we have dissolved, they have shown us that there is a change in color. The change in color or the dissolving, rate of dissolving, we have concluded that rate of dissolving is faster with increase in temperature, and it is slower where the temperatures are low. That one. But we have said that there are also some substances that we can put in a liquid. We don't observe a change in color, but we can observe something else. And I'm asking what else can be observed? If you don't see a change in color, you have mixed substances, what else changes? That's what I was asking.
Oh, okay. Queen Esther, unmute and answer.
Okay, quickly to end this lesson, suppose you mixed sugar with water, what happens?
I think in Esther, seems not to be there. It's Atkunda Vanessa there. Atkunda Vanessa. Unmute and submit.
The test changes.
So the test changes. Is that okay? So dissolving will lead to several things. One, it can be change in color. Number two, change in taste. Is that okay?
Yes.
Okay, girls, I think that is what time allows us to handle today.
Mr.
Go
Sanjay,
back.
there was a question that is dust an example of sublimation?
Sublimation is totally a different explanation, because sublimation is the drastic change from solid to liquid to gas, solid to gas. The intermediate stage of liquid is almost unobservable. That is what sublimation is. So if dust quickly changes from solid to vapor, but that is not what actually, that is a powder. A powder is still a solid state. So that sublimation has not taken place. It is just that the particles are broken down to that the rock has been broken down to finer particles. That's all that has happened.
Then there was also another one. Why does a balloon put outside lose air faster than the balloon put in the house where there is no heat?
Difference in pressure. Yes, Mr. Sari.
Yes, Mr. Chakoin.
So well done.
Thank you, sir.
A balloon put inside a house, inside a room, and outside the house.
Yes.
So it will now depend on the temperature differences, I think, that are there in the two environments in which the balloon is put. But then it could also be pressure. But I don't know precisely what the question is. What is the teacher exactly saying?
Okay, the question. The question, the girl, why does a balloon put outside lose air faster than the balloon put in the house where there is no heat?
But losing air, because you see, the child might be looking at things from a different angle. Losing air as in shrinking, kind of.
Yes.
Okay. It could be different. We could really attribute it to pressure differences, most probably. But then the other thing could also be air, because outside, I imagine if there is a wind blowing over this balloon, when there's wind blowing over that balloon, it could keep carrying away those particles of air which are escaping, and consequently lead to more air particles now coming out. Nature will always try to have some kind of equilibrium, an equilibrium between inside and outside. So if they are being kept away, pretty much the same thing, which we talk about when we are talking about rate of evaporation. Evaporation will be higher, will have a higher rate when there is wind blowing over something. Or the drying of clothes. I think the same explanation could come in for drying of clothes. When you have clothes inside a house and outside a house, the ones outside are likely to dry faster because the wind blowing over them keeps on sweeping away those particles which are escaping. The same explanation I think could come here in that case.
Okay.
Mr. Sally, do I communicate there?
Yes, I think the girl has gotten, she was in the Gano Esther quad posted in the chat.
Yeah, so these air particles coming out, escaping from the fabric are swept away, and then more are encouraged to come out, so that in an effort to establish equilibrium, and in that we find that the decrease in size is going to be a little bit faster than inside the room, because inside the room, most probably you do not have that air blowing over or wind blowing over the balloon. I think that's the explanation I could offer there.
Okay, there's also Katrina. Yes, Mr. Chakon, there's also Katrina saying, do the different types of the air put in balloons affect the rate at which the air can get out of the balloon?
Yes, because different types of air would have different sizes. So that would now mean that if you have air molecules with bigger particles, then the air rate of escape through the pores might not be the same as when you have air molecules with smaller particles. So the size of the particles, yes, because by different types of gases, you're now referring to the sizes of the molecules. Some gases have bigger molecules, others have smaller molecules. Those with smaller molecules should be able to escape faster through the tiny pores compared to the bigger ones.
Okay. Thank you so much, Mr. Chakoni.
Thank you to Mr. Sari for coordinating that side. You did a great job.
You're welcome.
Yeah. So, Mr. Senjo, you are signing out.
Goodbye.